campus that don't need to flush using drinking water.
Well,
The other thing is cooling towers. So we'll go up and see the cooling tower on this building.
Yeah.
And
Why not use it there?
there's no reason you can't do it.
You know, I live in a development in Winchester Commons, which is off of where Hollister and where they all come together there.
On the north side?
Yeah.
Yeah.
And they promised us reclaimed water for
Yeah.
development.
Yeah.
But it runs under the freeway, and so they have a conduit for it. But until that fire station gets built on the corner there,
Yeah.
they don't want to open it up. So we're waiting for this fire station, which was supposed to be built when that development, the Hideaway, was done.
Yeah.
It's been 5 or 6 years.
Yeah,
so
yeah.
We may never see it.
Yeah.
That's a problem.
Do the wisterias fill in a lot over spring? Or
Not really.
No?
Not really. I think everyone, they do, I know. I think everyone kind of was hoping they would, 20 years in, they'd be full, you'd get kind of full coverage, but you don't really see them on like the horizontal members. I guess you do a little bit on the top, but yeah, they kind of always have been this scraggly.
Are they just in planters?
They are, yeah. If you want to take a look, we can walk by there.
Maybe they need a town spot.
They should do food crops.
Yeah.
It might just be all root bound.
You plant some, what do I have at my house? Passion fruit.
Oh, yeah, there you go.
Oh, that would go.
Yeah, totally. I would love it.
Maybe a little too much. Okay, we're gonna go over here. We're gonna go up these stairs. Hopefully everyone's good with doing a few flights of stairs. We're gonna go up onto the roof, take a look at some of the rooftop equipment.
Do you know what all the keys on your keychain go to?
At this point, like, it's scary that I mostly do.
I know, we were saying that we probably have a master key that opens everything, so you don't have to do that.
If you're like the really important guy on campus, you do, but this is what I got.
Patrick, you need to tell Rodney to get new camera batteries.
Yeah.
Yeah, only one battery now.
Yeah.
Oh, you having to like power down and power back up?
One of them just died.
Oh,
We just need a new camera. That one just too.
Go to Best Buy, buy a new one, charge it to school.
Yeah.
seriously.
Yeah. Yeah, I think it'll do.
It almost costs me two schools.
Well, we do enough field trips with all the classes combined to warrant it.
How old is that one?
Well, I don't know. Did Rodney ever say how old that was?
I don't know.
It looks like ones I was using 10 years ago.
Yeah.
It seems like batteries only last a year or two before you gotta replace them.
All this work for my call.
Yeah, he's missing out.
Okay, one more.
Hey, you can make a 12-hour drive here.
For this.
Kids were climbing out here onto the roof. We had to do this recently.
Really?
Oh yeah.
Who's climbing on the roof?
Whoever, yeah.
Yeah, I can see that.
These steps are a little weird.
The heights of all stay down with you guys.
I should have asked.
Well, you said we're going to rooftop.
Yeah. That last set is definitely not.
Yeah.
It's weird because you do like 9 sets before that, and that one really throws you off. Thank you.
So why such a big gap?
Yeah.
That's
You mean
a lot
what?
of expansion, right?
Why are those stairs? Oh, yeah, yeah, I don't know. The question probably is just for earthquake, seismic.
I think someone with a little tip.
Yeah. They're pretty new actually.
Oh yeah, I don't remember those.
Yeah, maybe like 5-6 years.
Okay, what program uses them?
I think it's just the same one that was there before. The biology probably.
Okay.
Yeah. So this is the like the OG solar system, right? This kind of goes around the whole building. We'll go to the other side and you'll see it. But at the time, nobody wanted to see solar panels. So they made a huge compromise by putting the things flat, right? And building these curbs around them. So, I mean, not like you would not do solar like this today. A, it's inefficient. If you tilt these things to the south, you get a lot more generation. But B, every night when the fog rolls in, any kind of dust in the air or anything settles on these and they get dirty. So until you have like a 10% angle on these, they kind of can drip and clean themselves off, but don't put your solar panels flat. You're gonna have to clean them, you know, once a month. So there is somebody who comes up here and they got spigots that they come up and clean with. Non-potable water spigots, yeah. Again, one of the only buildings that's plumbed.
Would see them if they were propped up.
Yeah, but I don't know. They still didn't want them.
Right, too much of a taboo back then.
Yeah. So yeah, this is all new HVAC on this lab building here.
Yeah, lab's got to have that stuff.
Yeah, that's a good point. Is we have a lot of laboratory facilities on the campus, and anywhere you have chemicals in a space, you've got to ventilate at a very high rate, and you've got to exhaust 100% of the air in the space directly to the outside. In classrooms, offices, most of our buildings, we recirculate a good portion of the air. Unless the temperature outside is perfect, then you can get free air conditioning on a day like today. They call it economizing, right? So most buildings, though, they recirculate because you don't want to have to heat or cool a whole lot of, you know, cold air or hot air. Labs can't do that, and that's the big reason that they use so much energy.
Well, so they're assuming they've worked this out that the chemicals in the air will disperse.
Good question. Let's go look at the exhaust fan.
You know, get them out of the lab and
Yeah.
in public.
Yeah. No, I hear you.
I mean, it's like everything. It's such a big air, like the ocean.
Yeah.
You think, oh, everything will blend easily.
Yeah.
We'll find out that it's so.
So, and you know, that's a good point. I'll talk about the exhaust fan here for these guys. So yeah, I mentioned that if you're in a lab building, which we are on top of a lab building, you got chemicals, you got fume hoods. Those chemicals are supposed to stay in the fume hoods. Those fume hoods are going to have a dedicated system that's going to exhaust all that air out of the building. And it's got to be pretty beefy because there's also air handlers that are bringing air into the building. And the last thing you want is for that exhausted air to get sucked right back in the building. So that's why you see these exhaust fans are typically pretty tall, and they've got really powerful motors on them. You've got to get the air up to 3,000 feet per minute to get the nasty stuff high enough up into the air. Not all the time. On a day where it's really calm and there's no wind going, you can ramp that down, and you can expect those chemicals to go up into the air and disperse before they have a chance to get sucked back into this building's ventilating system or the neighboring buildings, or blow across the playground, across the street, whatever it is. But on days where it's windy, and depending on what direction the wind is going in, you've got to jack the exhaust rate up pretty high. Those are the exhaust fan stacks. So those brown things at the bottoms of them are the fans themselves. Yeah. So they're sucking air out of that box, that big box, which is connected down to all the exhaust ductwork in the building, and blowing it way up in the air. That little thing sticking on the side, that's a bypass. So when you've got a variable air volume ventilation system, which most modern lab buildings are, to save energy, right? Think about all those fume hoods. If you go into one of the labs and you close the fume hood, you don't need to be sucking as much air in. And if everybody goes into all their labs and closes the fume hoods, which is where they're supposed to be when you're not using them, then that system doesn't have as much exhaust to pull through, but you still got to get the air up out of the stack at a rate that's high enough that it won't cause problems. So that's what that bypass does. So if no one's here and it's the weekend, all the fume hoods are closed, but there's still chemicals being exhausted out of all the labs in the building, those brown fans aren't working as hard because they're not pulling as much pressure out of the building. That auxiliary fan will kick on and say, okay, I'm going to give you a boost just so you get all that air. I'm going to add air, and I'm going to get that velocity up to get anything that was in that exhaust system up and out and away from the building. So that starts to make you think about, like, okay, well, can you start doing things that are like dynamic. If you could measure real time what the wind speed and direction is, you could start to control these things and you could save a lot of energy.
Well, that's what I was going to ask. Do they have an anemometer or something that does this automatically?
Yes.
Leave it up to the
Yeah. So there's, if you just have a dumb lab building, chances are you're going to have to just go to that 3,000 feet per minute all the time. But then on a nice day where it's calm, there's not a lot of wind, and say the wind that there is blowing right out to the ocean, I should be able to get that rate down, turn my fans way down, and still not put anybody in danger. But I need to know what the wind is doing at all times and be able to make adjustments. So, you know, we've got 40 or so lab buildings like this on campus with systems like this. So we've got one central weather station, you know, really beefy, like industrial grade weather station that is connected to our building automation network that tells all these systems what the wind is doing at any time, and runs some math and says, okay, this is how hard you have to blow based on the current conditions. Saves hundreds of thousands of dollars a year.
Right, it does it automatically.
Yeah.
It doesn't need a person.
Yeah. No, it's programming effort. You know, you got to build a model that says, you know, here's how to operate for this building to be safe given this condition across all 360 degrees, across all wind temperature or wind speeds. So it's a lot of work on the front end, but you know, you do a project like that once, you save energy for years and years. So that's the exhaust system. This big thing right behind us right here is the cooling tower that's connected to a chiller that's in that room right there. So this does evaporative cooling, right? So
It's like a big swamp pool.
yeah, exactly. So you get condenser water from the chiller. So basically the chiller is handling the air conditioning loads in the building, sucking the heat out of the building, but it's got to send that heat somewhere. So it sends it as warm water to this cooling tower. There's a fan in there and some nozzles that basically let the water drip down this filtration media. You get a big fan, blows air across it, and it brings the water down, say 10 degrees, and sends it back to the chiller. And that's running continuously when that chiller is running to get rid of heat, right?
Does it make the moisture levels really high inside though?
No, because this is a closed loop going to the chiller. The chiller's got another closed loop that's sending chilled water around to the building, right? So everything on the cooling side is just chilled water piping that's going to, you know, it's going to the air handlers. The air handlers are blowing air across it. It's going to any lab equipment that needs to be cooled continuously. So you'd expect a system like this to be running most times. This particular plant almost never runs, and you can see it's in, you know, that filtration media is looking pretty crappy, and we've kind of let this plant go because it mostly doesn't run. We've got 11 other plants this size or bigger on the campus, and they're all connected. A big chilled water loop runs across all the lab buildings on the campus, and so this thing feeds the building we're on, but it also feeds into, you know, big 16-inch chilled water piping that runs around the whole campus at 42 degrees. So most of our buildings don't need a dedicated air conditioning system because they just take water from that loop. So they take it at 42 degrees, they send it to the air handler, anything that needs cooling, and then they send it back at 54 degrees, and they're doing that continuously. So
when the original buildings were done, they connected, the units were connected underground, or maybe?
The chilled water loop is only about 20, 25 years old. So we have a lot of buildings that are older than that. So it used to be every building had its own chiller.
So it's above ground. You can probably see it as you walk around.
Above ground, like sometimes some are in basements, some are on roofs, like this one's. Some are some are on the first floor, but they're all different. It's kind of like having a central plant. Like a lot of colleges have a central plant where you have one massive chiller, or, you know, set of chillers, and then you have that loop that goes around. So we basically have a dozen central plants. And that system has grown over time, and it, you know, kind of evolves depending on what the needs are and what new buildings are coming online. And
do you know what the media is in this?
It's just plastic, some kind of plastic. Another interesting thing, so skylights. So we are standing, the fourth floor is directly below us, and these three big skylights open up to, it's like a library that's, you know, takes up most of the floor. And they're facing north because, like we talked about, you want the light from the outside, but you don't want the direct solar penetration. So it tends to be, if we have skylights, they'll be kind of point it in that direction if we can help it. There's probably nobody in the building right now.
It's got white walls that it bounces off of.
Yeah, like a chimney. Well, let's go to the other side because that's the $1 million view over there. So this is another little exhaust fan. This is just for the bathrooms, and you know, you'll see these all over the place.
Oh, come on.
Ah!
$1 view.
There it is.
Yeah, that's nice. Jeez. What a canvas.
Because they're slumming it out here.
I know, right? So you can see all the PV panels down there on the office section too. So in total, this system's about 50 kilowatts. The one on the parking garage is about 800. The biggest one we have is about 2,000 kilowatts.
Where's that?
Where's that?
It's a big